Hi there, this is Professor Eckhouse, and I'm going to talk today about domain and range. So there's a lot of important information in terms of definitions and concepts, as well as lots of examples that I'm going to give you of specific kinds of problems. So if you'd like, again, to know what it is that we're doing, here it is. All right, so we're going to start with talking about one-to-one functions. First, we have talked previously about how to know if a relation, that means a relation between two sets of numbers, right? One input and one output. How do we know if that's a function? Well, think about it. Do you remember? There is one output for each input. And it passes the vertical line test. In other words, a vertical line going through the function would only pass through it one time. Any more than that, and it's not a function. All right, so what is a one-to-one function? So a key part of this statement right here is the word function. So we know that it must be this, right? There must be one output for each input, for one thing. But what is the one-to-one portion of it? So the one-to-one portion says, this part right here, means that there is one input for each output. Compare and contrast that to what I wrote in purple. Okay, so there's one input for each output. There's one x value for every y value. So this we can use what we call the horizontal line test. All right, so we'll come back to that here in just a moment. All right, so take a look at these three examples here. We've got the first one is a function. The second one is a function because every input leads to an output, and that output, there's one output for every one, right? So, sorry, I got a little tongue-tied there. For every input, it just has one output. Notice this over here, this input, has two outputs. So that is not a function. Okay, that is not a function. So which one is a one-to-one function? And I'll say there's only one. So first, it has to be a function. So it's one of these two. It can't be this one because it's not a function. Okay, so first it has to be a function, and then it has to be one-to-one. So if it's one-to-one function, that means that there is a one-to-one relationship between the numbers in the two sets, in the inputs and the outputs. There will be none of this and none of this happening. Okay? All right, so using a table to determine whether a relation is a one-to-one function. So first we have to determine if it's a function, and then we have to determine if it's a one-to-one function. But really, with something like this, it's easier to just say none of the numbers could be listed more than once, right? Unless it goes to the same number. So I'm just going to scan down through these numbers, and I'm going to see if I see any duplicates. Well, here I don't see any duplicates in the inputs, so every single one is different. But let's look at the outputs. Do you see any duplicates? So here's a 3 and here's a 3. And that means that 5 can lead to 3 and 12 can lead to 3. So that is not a one-to-one function. All right, so take a look at the second one and see if you think that one is one-to-one. All right, so if you look here, nothing is repeated. 2, 4, 6, 8, 10. And if you look here, 6, 12, 18, 24, 30, nothing is repeated. So this is a one-to-one function. Kind of looks like a line to me. Okay. All right, so you need to know what horizontal and vertical is, and a lot of people have a hard time remembering the two, and I remember back in the day I really had a hard time remembering which was which. So here's a picture. Where is the horizon? Hopefully you say it's right there. And that is what we call the horizon in a landscape. And so that's where the word horizontal comes from, basically. I don't know which one comes from which, but they are related. They mean the same thing. They have the same base. So vertical is then this direction. This is vertical, and it is perpendicular to the horizontal. In other words, there's your XY axis, okay? So remember that the horizontal is the X, and it is the input. And the vertical is the Y, and it is the output. Okay, so let's think about horizontal and vertical line tests to determine if something is a one-to-one function. So remember, this one, let's do purple for this one. This one is vertical, and this one will tell us if it is a function. Is it a function? Now remember, the test works where if it passes through the function more than once, then it is not a function. Okay, so here's an example. Is this a function? Is that a function? This is some sort of form of x equals y squared. It's been shifted and stuff, so I'm not going to write that down. It's something similar to that. So if I took that vertical line and I moved it over, it would go through more than once. So no, that is not a function. So it's definitely not a one-to-one function either. So first you want to see if it's a function. If it does not pass the function test, then it's not a one-to-one function either. All right, so let's try some others. So let's talk first, though, about horizontal. So make sure you've got this in your notes. Horizontal line test basically says, is it one-to-one? Now, it does not tell if it's does not tell us if it is, well, that's hard to say, a one-to-one function, just if it's one-to-one. This one down here, the vertical line test, tells us if it's a function. So to be a one-to-one function, it must pass both to be a one-to-one function. One-to-one and a function. All right, so let's look at just a straight line. Is that a one-to-one function? Well, first, does it pass the vertical line test? If I move that vertical line across the whole thing, would it ever cross more than once? No, it wouldn't, so it does pass. So that is a function. So that is a yes on that one. Now, does it pass the horizontal line test? And if I move that up and down, would it pass through more than once? It would not. So yes, it is one-to-one. So yes, it is a one-to-one function. It's both. All right, so let's try something. Let's try one more. Let's do quadratic. So it's parabola. So is it a function? So could I draw a vertical line here, or here, or here, anywhere I want? And yes, it is a function because it only passes through. I'm going to get rid of some of those. It only passes through once, no matter where we put it, it only passes through one time. All right, so now the next question, is it one-to-one? So let's draw this. No. The only place it would be considered one-to-one is at that point right there, right? But everywhere else, we draw a horizontal line, right? It passes through twice. So no, it is not one-to-one, which means it's not a one-to-one function. Not a one-to-one function, because it's not one-to-one. It's got to be a function, and it's got to be one-to-one. All right. So think about what something might look like to be a one-to-one function. And there's a lot of things it can't be. A lot of things. So there's very few things that pass the one-to-one function. All right. So let's move on. So we're going to find the domain of a function. So the domain, remember, and this may be new to you, but it is all possible input values. Every single thing, so every possible x value. When you say, well, what would make it impossible? We'll talk about that in just a minute. So the range is all the outputs, that is the y values that occur from the x values. All right, so all outputs that occur from the possible input values, in other words, the y values that occur from the x values. All right, so what is a polynomial? A polynomial, if you're looking at the graph, is a constant, uninterrupted, curvy line, or straight. It can be a straight line, which is just something like that. But it can also be that, and it can be, oops, not that. It can be that or that. Okay, so curvy, and it never has any breaks in it, and it doesn't have any sharp corners. Okay, so something like that, not a polynomial. Not a polynomial, because it has a pointy part right there. Okay, something like this, and then it goes on. There's a break there. That is not a polynomial. So polynomials are things with where it has like x squared or x to the fifth, and y to the third, z to the fifth, things like that. Okay, so the exponent is a whole positive number, and I mean the exponent on the variable. The exponent on the variable. Okay, so it couldn't be negative and it couldn't be a fraction. All right, so what is the domain of a polynomial? Well, look at all these pictures I just drew, and the domain is all the possible x values. If I draw this or that, is it ever going to stop? Is there ever a place where x can't be? And the answer is no. It's all real numbers. Okay, so all real numbers is one way to say it. The symbol for that in inequality notation, it looks like that, all real numbers, it's a fancy R. In interval notation, we say from negative infinity to infinity. Okay, so all real numbers, 3 different ways to say that. So all polynomials. That means quadratics, cubics, and everything up from there. All right, so let's find domain and range from a graph. So remember to ask yourself, what x values can this function have and not have? Okay, so remember the domain is all possible inputs or x values, and the range is all possible outputs or y values. All right, so when you see one of these graphs that I have printed from Desmos, you assume there are arrows at the ends. Okay, it just doesn't put them, but they're there. They go forever. All right, so the domain and the range. So the domain is all of the x values. So remember, this is the input or the x values. And this thing goes on and on to the left and to the right forever. So the domain is all real numbers. Oh, that was a terrible R, sorry. Or we could say negative infinity to infinity. All right, so what about the range? What are the y values that you can see happening here? Well, I see them all, right? All real numbers. Or we could say negative infinity to infinity. All the numbers. Okay, so that's a straight line. The domain and range of a straight line is all real numbers. All right, the next one is a quadratic. This is a parabola. It's facing downward. We're going to put our arrows on it. And if you're taking notes on this just on paper, you know, you can just go like this. It doesn't have to be anything fancy. You don't have to put the numbers on there, anything like that. So let's see, the domain. And I put this, actually this one number right here is important, that number. You need to put that, that's the vertex, okay? So I'm gonna highlight that in yellow. All right, so the domain. What is the domain of this? And I want you to think about it for just a second. What did I just say about the domain of all polynomials, this being a polynomial, right? It is all real numbers. Or we would write that as negative infinity to infinity, right? So we're going to do this in interval notation from here on. So what about the range? Okay, so the range, remember, is this portion here, up and down, there and there. But we always want to report the range from smallest, just like the domain, to largest. Okay, smallest to largest, from the bottom to the top. Okay, I'll write that too, bottom to top. All right, so this thing has arrows. It's going down forever and ever and ever. So the lowest point is negative infinity. Now, what is the highest y value? Now, be careful. People miss this all the time, including me. So be careful. This thing goes up and touches this point. What is the y value at that point? And that is 3. Okay, so from negative infinity, infinity always gets round brackets. It does touch 3, so we're going to put a square bracket. Okay, did you get that right? Possibly not. First try. Keep trying these. There's lots of little details, and every little detail matters when it comes to this kind of stuff. All right, so let's try this one. Why don't you pause the video? You know what a domain and a range are now, so pause the video and see if you can get this one right. And I'm going to put that there is a point right there. All right, so the domain is going to be the x values. Just trying to decide how to explain this. The x values. So where does it start on the x-axis? The farthest left point. Remember, we always go from smallest to biggest. So the smallest point right here is -4, and it goes forever to the right to infinity. Okay, so the domain goes from -4, and it touches -4 all the way up to infinity, and it never touches infinity. So, okay, so that's the domain. What about the range? So the range goes from here up to where? Well, this has an arrow on the end of it. I'm gonna make that purple. Has an arrow, and it's going up slowly, but it is going up, and it's going to go up forever. So the top of the range is infinity, but what is the bottom of the range? What is the bottom of the range? So that is going to be right here at -3. All right, so we go from -3. Does it touch -3? Yes, it does. It does include the number -3, and then it goes up to infinity. All right, so I want you to take a moment. I want you to try to think about the x values go from -4 to infinity. Look, -4 plus 4 would make a 0 there. Anything smaller than that, we couldn't take the square root. Think about that, because we are going to get to that here in just a moment. We could not take the square root of a negative, right? We can't do that. It must be 0 or positive. So it starts at -4 and it goes on. None of the numbers over here are in the domain, because they would make what's under the radical sign a negative. All right, so what about the other part of it? What about this -3 here? That has to do with this shift right here. There's a transformation, and it has shifted it to the left. I'm sorry, not left, down. Whew. All right, down. Those are the kind of mistakes I really hate making in videos because it's hard to fix. Okay, so it shifts it down by 3, and that's where this down right here comes from. Okay, let's try another one. Just asking for the domain. So I'm going to put some arrows on here. These go on forever in all these directions. And I will tell you that there is an asymptote right here where neither of these touch. And that place is at -3. Okay, so this place is at x equals -3. And I want you to think about where -3 came from looking at this equation right here. Where did that come from? Why would -3 make it have no output? Well, let's talk about that. So if I put -3, so if I said g of -3, I would have 2 times -3, no problem, that's -6. And on the bottom one, I would have -3 plus 3, which is 0. We can't divide by 0. It gives us an undefined answer. So at -3, there is no domain. We can't put x in. So x is everything else because the arrows go left to right, but not at -3. Okay, so how would we say the domain for that? So the domain is going to start at negative infinity. So remember, we always go left to right or bottom to top if we do the range. So starting at the very left, we're at negative infinity. And then we come to the right and, oh, we get to negative 3, and that can't be included. And then we have that union with, just like we did a couple weeks ago with lines. And then we've got, the next one is also going to be negative 3 up to infinity. So it comes into negative 3 on both sides as close as possible, but it doesn't touch. So that means infinitely close, and that is called an asymptote. All right, so what makes an input impossible? So this was an impossible input, right? Negative 3. Couldn't do it. So think about it. This is called a restriction on the domain. If an input is impossible, what we call it technically is a restriction on the domain. There are two types of functions we're going to see in here with restrictions on the domain. They are rational functions and radical functions. This is a rational function. Okay, and a radical function, I'll show you what that looks like too. All right, so a rational function is something like, let's just say f of x equals x plus 5 over, I don't know, x minus 1. That's just an example. But it's basically a rational function is like a rational number. It's a fraction, and it has x values in the bottom. Okay, x values, let me make a note of that. X values in denominator. Okay, there might be more than one, but usually you'll just see one in this class. All right, the next one, a radical function, has a radical in it, which is, something like that, a root. All right, so let's just say this one might be g of x equals the square root of x minus 3. So in this case, the x values, or value in this case, under the radical sign. Okay, so those have restrictions, and we saw a couple of examples of that. This one has a restriction because it's a rational function, and you can't divide by 0. This one has a restriction because it's a square root, and you can't take the square root of a negative. Okay, so those are our restrictions, and those are the only ones you need to know. All right, example 4, restrictions to domain of rational functions. So this is pretty much the next topic here. So as you can see on this one, f of x equals 1 over x. It's a rational function, like a rational number. It's a fraction, and x is on the bottom. And what does it look like? Well, just like similar to the one we just saw up above, has the same basic shape. Okay, so if you see something that looks similar to that, it's a rational function. It has an asymptote. So where's the asymptote here? The asymptote is right here on x equals 0. Well, that is because x is by itself. So x cannot equal 0. So how are we going to report that as a domain? You can think to yourself, what can x not be? Well, then turn that into what can x be, right? Remember, the domain is what can x be? What can x be? Right, that's the domain. All right, so it can be everything but 0. So how do we say that? We say negative infinity up to 0, union with 0 to infinity, making sure, again, that both of these are round, because that means we're not including 0. Okay, so all numbers except for 0 is what that says to us. All right, let's try another one. All right, pause the video and give this one a try. All right, so this is definitely a rational function because we have x in the bottom, but it's x minus 3. And what I want you to notice is x minus 3, and look where the asymptote is. The asymptote is here at x equals 3. Because if we had x minus 3, it cannot equal 0. So if we add 3 to both sides to solve for what x can't be 3. And look at that. From the picture, it's the same thing. Okay, so x can't be 3. All right, so, and you don't need to use this not equal to if that confuses you. If you'd rather just say, what x can't be? X can't be this, right? So you can just say x equals 3 is what x can't be. If it helps you, you can do it either way. I like not equal to because I just have to write less words. So, all right, so x equals 3 is what it can't be. So we're going to say that the domain goes from negative infinity up to 3, union with 3 to infinity. So it can be all numbers except for 3. And remember, these must be round. Okay, let's try this next one. So again, give this one a try without me. All right, again, rational function, because there's an x on the bottom. Notice that it's x plus 2, but look at where the asymptote is. The asymptote is right here at x equals negative 2, at that vertical line. All right, so if we have x plus 2, and we know that this whole thing right here cannot equal 0. So we subtract 2 from both sides, and we get x equals negative 2. Same thing as we got from the graph. Okay, so sometimes you won't have a graph. What if that graph wasn't there, right? What if it wasn't there? What would you do? And you didn't have any way to graph it. So you need to be able to do it algebraically as well. But I want you to be able to connect the picture to what the rational function looks like. Okay? All right, so 1 over x plus 2 has an asymptote at x equals negative 2 because negative 2 is going to make the denominator 0. All right, so the denominator then is all the things x can be. So x can be from negative infinity up to negative 2, union with negative 2 to infinity. After you write it, stop and make sure it makes sense. You have written this from smallest to biggest, right? And these brackets right here are round, which means that's the only time you could use union. If these were square and you said union, that would make no sense whatsoever. Think about why. All right, let's try the next one. All right, what are you going to do with this one? Because the asymptote is somewhere, oh gosh, somewhere in here. I don't know exactly where. It's kind of hard to tell because this thing didn't get close enough to be able to tell where it is. So now we're going to have to use algebraic methods to figure this out. We know that this bottom part cannot equal 0. The whole 2x minus 5 cannot equal 0. Now a lot of people jump to, well, x can't be 0. Well, that's not really true because you would have 1 over 2 times 0 minus 5. You'd have 1 over negative 5. That's fine, right? So I'm going to erase that. Don't write that down because that was an incorrect way of thinking about it. Okay, so make sure you understand that 2x minus 5 is the part that can't be 0, the whole thing. All right, so let's take that 2x minus 5 and set it equal to 0 and solve for x. Okay, so that's the best way to do this. So we're going to say plus 5 on both sides, and we get 2x equals 5. Now we need to divide by 2. We're solving for x. And we get x equals 5 halves. Now stop. Does that look about right? 2.5 is right here. So I missed a little bit, but that was pretty close. 2.5, 5 halves. Same thing. We usually leave it as a fraction. All right, so the domain goes from negative infinity up to 5 halves, union with 5 halves, up to infinity. And that's your final answer on that. Okay, let's try one more of those. You try this one without any help. All right, so this one is similar. Again, we look and say, oh, it's somewhere in here. It's hard to know exactly where. So we're going to say 3x plus 4 can't equal 0. All right, so we've got, let's just solve that. 3x plus 4 equals 0 and find out what x is. Okay, so let's switch colors. Negative 4 on both sides, so subtract 4. And we've got 3x equals negative 4. Now I'm going to divide by 3, and I get x equals negative 4 thirds. So negative 4 thirds is about negative 1 1/3. That looks about right in there somewhere. Okay, so now the domain is going to go from negative infinity up to negative 4/3, not including either one, union with negative 4/3 to infinity. All right. Now, what if we have restrictions to the domain on a radical function? And a radical function, remember, is any even root. That's what we're talking about here, because odd roots, you don't have limitations. They can be negative. So if I took the cube root of a -8, for instance, the cube root of a -8, I would get -2, and that's fine. But we cannot take the square root of -9, right? There's nothing we could get that would be the square root of that. So that's why that's restricted. All right, so the square root of x, I'm giving you a picture right here, starts here and goes forever to the right. But let's do it algebraically as well. So we know that what's under here must be 0 or positive. So how do we write that must be 0 or positive in math speak? Well, we can say greater than or equal to 0. Greater than 0 is positive, equal to 0 is equal to 0, right? So we can say x is greater than or equal to 0. And that's in inequality notation. Now we need to put the domain in interval notation. Okay, so greater than or equal to 0 is said like this, 0 to infinity, like that. Now look at the picture. Does that match what you just wrote? Hopefully it does. Yeah. Okay, so that's how you think these through. It must be 0 or positive, and the key is to write this thing underneath is greater than or equal to 0, whatever that thing is. So let's look at something that's a little different. And so that thing underneath the radical sign this time is x plus 3. So this whole thing must be greater than 0 or equal to 0. Okay, it must be positive because I can't take the square root of a negative number. So let's set that up and say x plus 3 must be greater than or equal to 0. So we're going to subtract 3 from both sides. And x is greater than or equal to -3. Now, was I supposed to switch the sign? No, be careful. A lot of people switch the sign when they subtract. It's only when we divide or multiply by a negative number we're subtracting. So this is an equality notation. Does it look right? Greater than or equal to -3. Well, here's -3, and it's everything greater than or equal to the -3. Okay, so that looks good. So now the domain is going to be -3 with a square bracket up to infinity. So these do not have a union. The rational functions have a union. The radical functions do not. At least the ones you're going to see don't. It's not true always, because sometimes it can get a little more complicated. All right, so this one is 4 minus x. Notice that this thing has flipped over. What caused it to flip over? Think about that. We're not getting into that quite yet, but think about it. Okay, so this thing touches at 4. Let's think about what's happening there. So we've got 4 minus x is greater than or equal to 0. All right, so let's rewrite that. 4 minus x is greater than or equal to 0, and let's solve for x. All right, so I'm going to subtract 4 from both sides, and I get -x is greater than or equal to -4. All right, now I need to multiply or divide both sides by a -1. So I'll just do this, multiply by -1. And I get x. Now this is when I have to switch this sign to be less than or equal to, because I just multiplied by a negative. And I get 4. Is that true? Does that work? Yes, it is all numbers, right? All going all the way, not that way, to the left, all the way over to -infinity. So let's write our domain as -infinity. Remember, always go, even though the arrow is pointing left, I know people often want to write it the opposite way. You want to just think smallest to biggest. So the smallest is -infinity. The biggest is +4. Does it touch at 4? Yes, it never touches infinity. Okay, so that's a radical function. According to what we did before, why don't you try this one? If you don't know how, you can let me do it and then try the next one, but give it a try if you want to. All right, so this thing touches right here, but this is 3. So that looks like 2.5 to me. So let's see what happens. All right, so we've got this must be greater than or equal to 0. So let's bring it out and deal with it. 2x minus 5, what's under the radical, must be greater than or equal to 0. So let's add 5 to both sides. And I get 2x is greater than or equal to 5. Now divide by 2. And I get x is greater than or equal to 5 halves, which is 2.5. So that looks good. Greater than or equal to goes to the right, so looks like we've got it. So the domain goes from, now it's bigger than 5 halves. So 5 halves is the smallest number, so we want to put it first, and it goes all the way up to infinity. It touches 5 halves, not infinity. All right, so now definitely try this one. All right, so this one touches there, and we're not sure from the graph what it's going to be, so we're going to have to do it algebraically. So hopefully you're starting to see a pattern here. So 3x plus 7, what's under the radical, must be greater than or equal to 0, must be positive. So we've got 3x plus 7 is greater than or equal to 0, subtract 7 from both sides. 3x is greater than or equal to negative 7. Do not switch the sign, because I didn't multiply or divide by a negative. Divide by 3. X is greater than or equal to negative 7/3. Does that look like negative 7/3? Negative 7/3 is 2 1/3. So, yep, negative 2 1/3. Looks good. And it goes to the right. So this thing's going bigger, right? So it's greater than or equal to. So we're going to write our domain as negative 7/3 is the smallest thing that this thing could equal. It can equal negative 7/3, and it goes up to infinity. Okay, find the domain when you have to figure out the restriction. So example 6 shows us what kind of a function. F of x is x squared minus 16. So this is a whole positive number, so this is a polynomial. And what did we say before about domains of polynomials? There's no restrictions. No restrictions. That is thunder happening at my house right now. All right, so that means that the domain is all real numbers. And remember, the way we say it in interval notation is negative infinity to infinity. So if you're given something very straightforward like that, which you will be, make sure you understand a polynomial has all real numbers as the domain. All right, example 7. So we've got what kind of a function? Rational. This is a rational function. So this one is going to look something like, maybe like that-ish. So maybe it's flipped over, we're not sure, but there's going to be an asymptote somewhere in there. And I'm not going to worry about that. It's as much as I'm going to do with it, because now you need to know how to do this just algebraically. All right, so we've got 4 minus x. This whole thing cannot equal 0. So let's set that equal to 0 and solve. All right, so I'm just going to add x to both sides. That makes things easier and faster. And I get 4 equals x. You could just think through it and think, what would I put in right there that would make this thing equal 0? I would prefer that you actually be able to do that and think through that and not always have to just follow a set of steps. So just think to yourself, x must be 4, right? Because 4 minus 4 is 0. All right, so x equals 4 is what x can't be, right? It can't be 4. So what is the domain? The domain is going to be negative infinity up to 4, union with 4 to infinity. All right, so this thing, as we can see now, is actually shifted over to where this is 4, and then we have this one here and this one here. So that's what it actually looks like. Okay, another one without a graph. So see what you can do with that. All right, so we've got a radical function. So this is the part that we're dealing with. And that part right there must be greater than or equal to 0. All right, so we've got 5 minus x must be greater than or equal to 0. All right, so how are we going to do this? A couple different ways. Let's keep x on the left. Minus 5 on both sides. And I get negative x, don't lose the negative right there, is greater than or equal to negative 5. But now we need to multiply both sides by negative 1. And we've got positive x. Now, then what do we need to do? We multiplied by negative 1, so we need to switch this to be less than or equal to. Negative 5 times negative 1 is 5, so x is less than or equal to 5. So just, if you're doubting yourself, think, okay, it's less than or equal to 5. What about 6? That's not less than or equal to. Let's see what happens. So we're going to say the square root of 5 minus 6. That's the square root of negative 1. Is that possible? No, it does not exist, right? So we can't put 6 in. So it's less than or equal to 5. All right, so the domain is all numbers less than or equal to 5. That means what? We don't have a graph to look at. So all numbers less than or equal. So what's the very smallest number less than or equal to 5? That's going to be negative infinity at the farthest left, coming all the way up to 5. You might find it handy to just draw this and say, well, here is 5, right? Here's 5. We want it to be less than or equal to 5. So this is how we draw it. We're just going to say negative infinity up to 5, including 5, because it's or equal to. Okay, so if it's or equal to, remember, we use this kind of bracket. I think that was the end of this. Thanks for watching.